Well, pre-calculus classes, as always, good morning, good afternoon, or good evening. We are going to finish up what is probably the longest section of information that we covered throughout the school year in section 4.5. And I know we've already spent several, days with graphing. The final thing that we cover within 4.5 is modeling trig equations, because some of the components of this involve the knowledge that goes along with graphing. So, first thing that I am going to do is just go ahead and rewrite the equation that we use that is going to come into play. And then, one of the things that is going to happen is occasionally there are sets of data that can be modeled using sinusoidal equations or sinusoidal models. And one of the things that definitely does that is the average temperatures for each month of the year. I mean, doesn't matter where you're at in the northern hemisphere, or the southern hemisphere, they're all going to form, if you were to graph these, a fairly sinusoidal pattern. Now, again, it's not exact, but that's by far and away our best option for modeling this data. Now, the other thing that when you have a set of data like this, the two things that you always want to start out identifying are your maximum and your minimum. So, probably not a huge surprise, the maximum temperature anywhere in the northern hemisphere is July. The minimum is January. Now, if we were to graph these, you don't necessarily need to graph these data points, because they are, when you actually have the X and the Y already given to you, there's less need to graph it. When we do the last example, you'll see where a graph really helps. But the other thing that I'm going to do is, if we were to graph, we would probably graph January on the y-axis. So, just for ease of calculating, we're going to actually, instead of saying January is month 1, we're going to say it's month 0. You could certainly do this as month 1. It wouldn't be wrong. So, the maximum occurs at 668.5 and 0, 18. All right. These 2 points we will use to find basically the amplitude, the period, the vertical shift, and your phase shift. Now, to find the amplitude, what you do is you take the y maximum minus the y minimum, divide by 2. So for this one, 68.5 minus 18 divided by 2 is, well, that's 50.5 divided by 2, 25.25. So that's your amplitude. Now, I know one of the things that you've noticed is I sometimes, with the notes, may go a little bit out of order from how they're printed. The reason, I really think it makes a lot of sense to find the amplitude and the vertical shift together. And the reason, well, the vertical shift, you simply take the y maximum plus the y minimum divided by 2. And so from here, 68.5 plus 18 divided by 2 is, this one I'll go ahead and use the calculator. It's not as nice and neat as just plain old 50. 43.25. So that's D. All right, period. Well, again, for this, yes, it's probably fairly obvious. 12 months of data, period is just 12 months. Well, it's not always going to be that cut and dried. The way that you find the period is, again, using your max and your minimum. The difference is for the period, because that's how long something takes, we use the x values. And we're going to take 2 times when the x max occurs minus when the x minimum occurs. Now, the reason why I use absolute values, it's not always going to be where the minimum occurs before the maximum. And the reason why you take these and double it is if you think about when we graph from a maximum to a minimum, that's only half of the wave. Like if it was cosine, from max to min, that's half. So here, we're going to take 6 minus 0, well, that's 12 months. And then, of course, with the period, we actually care more about b. So we'll set that equal to 2 pi over b. So 12b equals 2 pi. And divide. So b is pi over 6. All right, so those are your 3 things that are always going to work the same way. Now, your phase shift. You actually have to find 2 of these because all of our data can be modeled either as a cosine or a sine. Now, sometimes you may only be asked to find one, which then, if so, cosine's the easier one. The reason why cosine is easier is when we graph cosine, it starts at its maximum. So all you have to do is look at, okay, so the phase shift for a cosine function is simply the x maximum. So what's the phase shift here? It's 6. Technically 6 months, but again, for this, we're not going to be real picky there. So I'm going to go ahead and actually write out my first equation since I have all of the information. So y equals 25.25 cosine. B is pi over 6, x minus 6, and I would just leave it factored, plus 43.25. All right, we're not going to worry about the regression for now. So I'll actually put the other equation down here. Now, sine. Well, when we graph sine, it starts at a 0, goes to its maximum. Well, that is 1/4 of the way through the period. So what you have to do is you calculate 1/4 of the period. So 1/4 times 12. Well, that's 3. Now, that's when this should occur. Well, it actually occurs at 6. So the way you determine, and I'm not going to be able to write something nice and neat in this little bitty blank, but the phase shift for sine, you take when the actual max occurs minus when the max should occur. Well, when does the max occur? 6. When should it occur? 1/4 of the way through at 3. So here, 6 minus 3 is 3. All right, so y equals 25.25 sine pi over 6 x minus 3 plus 43.25. So you can see for your 2 equations, the only thing that's different is when that phase shift occurs. If you're using cosine, it occurs at the max 6. If you're using a sine wave, it occurs 3 months after when it, in theory, should occur. So that is that. And you could even do these other ways. You could have even said, if you wanted, you know, since the graph or the data starts at a minimum, we could have even said there is no phase change. You just had a reflection over the x-axis. So, I mean, you can even do the reflection for sine. That's usually not as easy, though. But, you know, there are usually 2 or 3 fairly, you know, equivalent ways of finding these equations. So, this first one always takes a little longer. The next one, because it's almost the exact same thing, will work this, you know, kind of like what we just did. The only thing that we're going to let you see is now in Chicago, which is a little bit further south than Maine. All of the temperatures are a little bit higher. As far as the maximum, though, is still July. The minimum is still January. So the max occurs at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. At 673, the minimum occurs at 0, 21.4. And that's where I was saying if you used 1 through 12, well, here's what's going to happen. These would have been 7 and 4. They just would have been shifted 1 over. So a little easier if you use 0 there. All right, so first, our amplitude. Well, again, y max minus y min divided by 2. So 73 minus 21.4 over 2. It's going to be a little bit more, 25.8. All right, like I said, I'm going to go ahead find D next, because all you do is you take those same two values, add them, divide by 2. .2. This is actually the average temperature for the year, so that's the reason. Again, Maine's a little further north, so it's a little lower than Chicago. All right, period. Again, yes, same exact. You take 2 times absolute value of the max for X minus the minimum for X. 12. And then, yeah, just even though you've already seen it, I'm going to go ahead and just that way, the more you see it, 2 pi equals 12b, divide by 12b, pi over 6. All right, so again, that's b. Now c. Well, again, we have to do 2 of these, cosine and sine. Again, cosine's your easy one. When does the maximum occur? Well, at 6. So our equation for cosine, y equals 25.8 cosine pi over 6 x minus 6 plus 47.2. Now, again, for sine, you take 1/4 of the period, so 1/4 times 12, yes, is still 3. It hasn't changed since the last example. Now, again, you take when does the max actually occur minus when should it occur. 6 minus 3. Again, I realize these were both going to be the same, so was this. But again, just, the more you see that, the more familiar you get. So, pi over 6, x minus 3, and plus 47.2. So, for those, we actually have 2 very similar examples. Now, the next one's going to be a little different. All right, here again, you have a pendulum. At time 0, they've obviously, kind of, in order to start it, they pull it one way or the other. And so at time 0, it's there. And so, again, what we need to do is go through and find our minimum. And let's see, where is our maximum? 2.8. Again, we don't really need to graph this data. So our minimum, 1.2 0.682. Our maximum is 2.8, 1.838. So first, let's find A and D. Again, for A, y max minus y min divided by 2. Definitely going to use the calculator here. .578. For D, we're just going to add those and divide by 2. .26. Now, here is why you always want to identify max and min. Because, this set of data, from 0 to 4, that's not going to be your period of 4 seconds. Sometimes they give you more data than a full period, which will be something we find here. So the period, again, you take 2 times 2.8 minus 1.2. Well, I know that's 1.6 times 2 is 3.2 seconds. All right, so when we take that equal to 2 pi over b. I like this example because this also allows us to talk about something else. 2 pi equals 3.2b. And when you take 2 divided by 3.2, here's what I actually like to do. That 0.625, go ahead, convert it back to a fraction. And it's 5/8. So b is 5 pi over 8. I prefer that to saying it's 0.625. We do not want you to leave it as 2 pi over 3.2. Don't leave a decimal within a fraction. All right, so the last two things. C. Well, again, for cosine, just when does the max occur? 2.8. For sine, we're going to take 1/4 of the period. 1/4 of the period is, you may or may not need to actually use your calculator there, 0.8. So it should occur at 0.8. It actually occurs at 2.8. So for sine C, we're going to take the 2.8 minus 0.8, and it's 2. So and again, these are technically 2.8 seconds, 2 seconds. So now here, I guess it actually says only one function. Sometimes we will ask you to find both phase shifts, maybe only write one equation. And then it's a matter of, you can pick y equals 0.578. I'll go ahead and write them both out. Sine 5 pi over 8, x minus 2. One thing you always do want to be careful, make sure that you do match the sine phase shift correctly and the cosine phase shift correctly. All right, final example. Now, kind of building towards this. We call this the tidal wave problem or a tsunami. Basically, it's a rapid change in the tide. It's a fast-moving ocean wave caused by an underwater earthquake. Water first goes down from its normal level. That's important. Rises an equal distance above its normal level. Period is 15 minutes, so that's kind of helpful there. They've also told us the amplitude is 10 meters. The normal depth is 9. So A is 10, the normal depth is 9. That's D. What's the average temperature? D. What's the average or normal water depth? D. All right, so period. 2 pi over B equals 15. So 15B equals 2 pi, so B is 2 pi over 15. Now, here is where we're going to also go ahead and graph this. And we're going to even talk about another thing or two that goes along with this. And I suppose we'll talk in a second here. I didn't really choose this well because, in all honesty, I don't need much in the way of negative here because the water, well, is never going to get below 0 depth. So, but, you know, as far as your X scale, you can really just go by 1. Now, it says the water starts at a depth of 9 meters. Now, it's going to go down first, go up. So basically, if it's the amplitude's 10, D is 9, that means our max is 19. Our minimum, which we'll talk about, is, if you take 9 minus 10, in theory, -1. So when I set up my graph, the way I've done this, let's see. I can actually go by 2's. So it starts at its normal depth of 9. Now, you know the period's 15. Well, so at 15, it's going to be back at its normal. Now, the other thing, we know as well that if it starts at its normal depth, ends at its normal depth in the middle, so this is 15, it's going to also be at its normal depth. So 15 divided by 2 is 7.5. So at 7.5, it's also going to be at 15. So when you're graphing, you know, we always want our 5 critical points. Now, we need the other 2. Well, this is at 7.5. Well, what's half of 7.5? 3.75. Now, it also says it is the amplitude's 10, the water goes down first. So at 3.75, the water is, again, in theory, going to be -1. So when we graph it, it's going to go here. Now, as far as this is 7.5, this is 3.75, well, the maximum is going to occur in the middle of these. So if you add those up, 7.5 plus 15 divided by 2, 11.25. And then our maximum will be 19 meters, which is right there. Now, that may not sound like a lot, but keep in mind, because this is meters, that's like 60 feet. You know, a 60-foot wave, that's pretty substantial. So, here's what we end up with. We now can set up our equations. Again, I realize here it only says 1, but we're going to at least talk about both. Now, C, again, for cosine. Well, when does the max occur? 11.25. As far as For sine, we're going to take 1/4 of the period, $3.75. Now, that's not C. You have to take when does it actually occur minus when it should occur. Whoops. And so when we do that, 11.25 minus 3.75 is 7.5. Which, in all honesty, you can maybe even see. You know, that's where the sine wave usually starts. Sometimes you'll even be able to see those if you graph. So I'm only going to write one of the equations. If nothing else, I'm kind of out of room here. So y equals, I'll go with the sine wave. 10 sine 2 pi over 15 x minus 7.5 plus 9. Now, predicting the water depth using our equation. Basically, all you're going to do is plug these in. Now, the first thing you do want to be careful about, 2 pi over 15. Make sure your calculator is in radian mode. And then here's where, if you just take 2 minus 7.5 in your head, if it's something easy, probably a little easier, and then you do always want to make sure that you've closed all of your embedded parentheses. Now, if you look at 2 seconds, you can see, yeah, my graph's not bad. It's around 1.57 meters. Now, to re-enter for 4 minutes, hit second, enter, and now what I can do, take 4 minus 7.5, well, that's negative 3.5. You know, you can just come back up here, and at 4 minutes, I get roughly negative 0.945 meters. Now, according to the model, and I'm not going to actually find all 3 of these. I figure if nothing else, you know, you guys can enter that in if you want. But according to the model, what will the minimum depth of the water be? According to the model, 1 meter. Now, how do you interpret this answer in terms of what will happen in the real world? Well, here's what's happening. Is now you would not want to actually be on the ocean or, you know, on the shoreline when this is coming in. You know, a 60-foot wall of water, that's bad. If you were, say, up in like a helicopter above this at a safe level, there is going to be a portion of time where the tide is so strong that you will actually see the ocean floor for what looks to be about maybe 2 seconds. So, you know, according to the model, what will the minimum depth of the water be? Negative 1 meter. How do you interpret it in terms of what happens in the real world? It means that, again, for a brief moment, you'll see the ocean floor. And again, that's a bad thing because that means we have waves at certain points that reach up to 60 feet. I mean, so, you know, and again, that's 30 feet roughly above normal. So that's how this works. So fairly involved, fairly long set of notes, but that's kind of what happens with the modeling. But that now finishes everything we're going to look at from section 4.5.